I wanted to recap the lesson that we did on lesson 5, representing exponential decay, and want to basically pull out some of the most important features and also some of the things that I know that can be confusing for students. So let's take a look, and I'm just strictly going to take a look at this with regards to the notes that we did. So we've got a situation, a real life situation, where you are a scientist and you are in charge of looking at algae bloom on a lake. And basically what you're trying to do is control the algae bloom that you're seeing on this lake by putting in some treatment products. So what the treatment products will do is control the algae that's growing on the lake. So basically, it's telling you that once the treatment begins, that the area that's covered by the algae in square yards is given by this equation. So you're given an equation that represents this situation. We know that A stands for the area, and the T, which is the exponent right here, stands for time, and time is being measured in weeks. All right, so what we're supposed to do is, in this equation, we're supposed to answer the following questions. What does 240 mean in the equation? So this amount right here, what does this mean? And what does 1/3 mean? Because they mean something. Whenever you write equations, numbers mean something. So that's what I want to make sure that you understand, because you're going to see this over and over again in exponential work. So let's go ahead and look at the first thing. 240. What does that tell me? It tells me that 240 is the starting amount, or what the lake has to start with in terms of algae before they even started treating this. So this means that the algae, I'm going to try to write it small, and I'm going to actually write it. I'm going to turn off the video, write it, and then I'll explain it. Okay, so you could see that I typed out or wrote out what the amount 240 tells us the amount of algae initially, so that's at the start, so initially found in the lake before they started treating it. All right, so they found 240 square yards. So this 240 is 240 square yards of algae. So that's really critical, because that is when time, and I'm actually right now just going to I'm just going to scroll up here, right here. This is at time 0. It's where I start. All right, so that is square yards of algae. So I just type that in, write that in right here. Square yards. All right. So now it says, what does the amount or the fraction 1/3 tell us? Well, it tells us that that is a fraction of the amount of area that is being covered from the previous week. All right, so let me go ahead and write that down. So let me see if I can explain this correctly or completely for you. So we know that we've applied a product to the algae, and every week that algae is going away, and it's always going away at a rate of 1/3 of the previous week. So this means that every week the area covered is 1/3 of the previous week, meaning the area is getting smaller and smaller, right? Because the product is working, it means that you started out with the 240 square yards, and after 1 week, it takes a third of it, and then take that amount and a third of it the following week, and a third of it the following week. So basically, I think I even mentioned in class that 2/3 is remaining. So if I am eating up a third of it, what's left? 2/3 of it. So again, it's always 1/3. That is the rate of decay. It is leaving by a rate of 1/3 of the previous week. All right. So then what we did was I had you open up Desmos, and we graphed in Desmos this table. And you could see here that I gave you the table of values. And how did this table of values come about? Well, you could see the 0. So when time is 0, look what I did. That 0 was put on the exponent of t. Here's 1, goes right here. So that means 1/3 to the power of 1. 2 means 1/3 to the power of 2. So that means when I go ahead and calculate the area, you can see I start at 240, I drop to 80. This is 1/3. So if I multiply 240 times 1/3, I get 80. When I take 80 and I multiply that by 1/3, I get 27. When I take 27 and I multiply that by 1/3, I get 9. And when I take 9 and multiply that by 1/3, I get 3. So this is a series of numbers that you can see keeps getting smaller and smaller and smaller. And I would do the same thing. If I took a third, if I took 3 and I multiplied that by 1/3, right, I'd get 1. And then if I did that and I multiplied that by 1/3, I'd get 1/3. And I'd keep going, and it would just get smaller and smaller and smaller, but it would never go to 0. So that means if I were to show you a quick graph, I would graph it like this. Along the bottom, again, we did this in Desmos. This is time. How am I measuring time? I'm measuring it in weeks. And what is on the y-axis right here? This is my area. So I can easily right now drop a point right here. And let's just say, I can say that that's when time is 0. So here's 0. And what is this? 240. Right? And so I can know that at 1, at 2, at 3, at 4, right? Take a look. I can do this and just start going. 1 is at 80, so if that's 240, I could see 80's maybe about here, and then we go here, and then here, and then here, and it's going to keep going just like this, just like I showed you in class. It's going to keep going closer and closer and closer to 0, but it's never going to get that. This is decay. The other thing I pointed out to you is that right here is the y-intercept, or the vertical intercept. This is where does it cross this y line, the vertical intercept. It means where did my graph start? At time 0, I had 240 square yards of algae in my lake. All right, so then what you would do is if I had this really nice graph right here, I would read the graph. So if this is week 1, this is week 2, this is week 3, what I would do is go to week 2.5, which is right there halfway between, and I would read the graph. I'd take it up to it hits the point, and we figured out that it would be approximately 18 square yards. So what I would do is take a look right here. If at week 2 it's at 27, week 3 is at 9, I would go halfway, somewhere in the middle between 27 and 9. All right, so that's what we did, looking at you being a scientist, you analyzing a graph, you analyzing a table, you analyzing what the equation is telling you, because you need to know, like, is my treatment working? How quickly is the algae going away? So this is critical. All right, then we looked at the next problem. And this next problem had to do with medicine, insulin. So insulin is taken by people that are diabetic, and this patient receives 100 micrograms of insulin. So you know somebody that's diabetic, they're taking insulin. In this particular case, this patient is taking 100 micrograms. Here's the graph that shows the amount of insulin remaining in the bloodstream over time. So take a look at it. I noticed that where did I start? I started at 100. And you could see that from 100, it dropped to 90. And then from 90, it dropped to 81. From 81, it dropped to 72.9. So, and it keeps going down, right? Even though I don't have any more numbers, but it keeps going down. It keeps going down in an exponential fashion. How do I know that? It says, how can I check the graph to know and support that the scientists have said that in the patient's body that this is decreasing exponentially? Well, we talked about it in class that some students said, well, I noticed that the graph is curved. So that's one way. Absolutely. They also noted that the numbers are not going down by the same amount each time. So let me just write that down, by the same amount each time. And I can verify that, and I really encouraged you, and I actually drew this on the board, is let's draw an X and Y table, right? And I know that I started out at time 0 at 100, and in 1 minute, remember we're looking at time in minutes, that I went from 1 to 90. In 2 minutes, I dropped to 81 micrograms. So every minute, look at, from 100 to 90, that's a difference of 10. From 90 to 81, that's a difference of 9. And then I drop down to 72.9. Well, that's more like, let's see here, a little bit more than 10, right? So, or less than that. So it's not consistent. Therefore, I know that this is exponential. So then it's asking you, well, how much insulin broke down in the first minute? Well, I went from 100 to 90. Well, how much is that? What is that amount? Well, you were asked that same question on the exit ticket. And one of the things I was encouraging or telling people to do is, what do I multiply 100 by to get to 90? Or you could say, if I ended up with 90 and I started with 100, what is this? This is 90%. So if this is 90%, what's remaining? What fraction is remaining? So if I look at 100 being 100% and 90 is 90%, well, what's the difference between the two? 10%. So how much insulin broke down in the first minute? 10% did. So in order for me to go from 100 to 90, This is 10% or 1/10. 1/10. That's what I got. How else can I do that? Well, if I take 90 over 100, and now I have 9/10, because all I did was divide the top and the bottom by 10, I get 9/10. So remember, if I were to draw a big square, and I know that this is 10/10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I have 9 of them, here's 1, 2, 3, 4, 5, 6, 7, 8, 9. What is left right here? What is left? 1 out of 10. So that's how another way you can look at it. So how much insulin broke down? What fraction of the insulin is that? It is 1/10 is what's remaining. All right, now, or that's how much broke down. What's remaining? 90% is remaining. So how much insulin broke down in the second minute? Okay, well, let's go up and look. I went from 90 to 81. So let's go up here. So 90 to 81. Okay, what do I multiply 90 by to get to 81? Well, I know it's got to be smaller, right? So let's do it this way. If I take 81 over 90, divide the top by 9, divide the bottom by 9, what do I get? What's 81 divided by 9? 9. What's 90 divided by 9? 10. Oh, look at that. I got the same amount. So what is remaining? 1/10 is remaining. Did you notice it's the same each minute? So basically, if I go up here, this means every time it's always 1/10. Always 1/10. This means it's exponential. It's one additional way. So if 1/10 is broken down every minute, what fraction remains? Well, we already answered that question. If, again, going back here, if I draw a box and I cut it up into 10, let's make sure I do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if I have 1/10 shaded in, well, what's left over? You can count. What's left over? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9/10 is remaining. That's what's remaining of the insulin for each minute that passes. This right here is what we're going to use as our decay factor. All right. So what that means is I can now complete the table to predict amounts at 4 minutes and 5 minutes by taking the minute of 72.9. Remember what we said. It's always based on the previous time multiplied by 9/10. And when I do that, I get, let's double check my notes here, I get 65.61 micrograms. Then what I'm going to do is I'm going to take 65.61 micrograms and multiply that amount by 9/10. And when I do that, it's always, remember, I always lose a tenth. So what's remaining? 9/10. So that is why I'm using the 9/10. So now what is that amount? 59.05. So now it says, well, what would I do to figure out how many micrograms it would be after 10 minutes? Well, I could continue my table, right? But I would have to keep multiplying this by 9/10, and again by 9/10, and that gets to be cumbersome. So what you could do is you could actually write an equation to help you. And that way you can, at any point in time, figure out how much there is left. So what would I do? Remember, we always start with the initial amount. How much did I start with? So I started with 100 microgram, right? That's how much was in my bloodstream. And how much is remaining each time? 9/10. And I can raise that to the power of t. This is my generic equation. So now I could easily find out what 10 minutes would be. I would go 100 times 9/10 multiplied by raised to the power of 10. And I would need to use a calculator to help me figure that out. So the big takeaways here are, you want to know what is remaining. So my equation that I write is always going to base on my initial amount. So what was the amount that I started with? Multiply that by the decay factor. Right? This is what's remaining. What remains. Okay, and I'm going to raise that to some exponent up here that typically relates to time. All right, so in the homework or in the exit ticket, you were asked to look at acetaminophen, and that's like Tylenol. And this person started with a certain number of milligrams. So you need to know, like, what's the initial amount that is being given to you in the problem. Then it says, hey, I think it was even 1,000 milligrams. So then it says, okay, well, and I can't remember how they're measuring time. So I went from 1,000 to 750. So what did I multiply 1,000 by to get to 750? Well, remember what I did was I took 750 and I put it over 1,000, and I can divide that. This is 75%, or 75 over 100, or 3/4. So right there, that is my amount. That is right, because that is what is left. This is what is my decay factor. All right? So you should, by this point, hoping to be able to use this growth factor, or the decay factor, sorry, it's not a growth factor, my decay factor, use the initial amount, and write an equation. All right, good luck. See me during office hours if you need any additional assistance.